lecture on chapter 5, and we want to compute the Jordan form. So given a matrix, square matrix A, so given a square matrix A, given a square matrix A, we want to choose M, we want to choose M so that M inverse AM is as nearly diagonal as possible, is as nearly diagonal as possible. So the simplest case is when A has a complete set of eigenvector. A has a complete set of eigenvectors and they become columns of M. They become columns of M. This implies the Jordan form is M inverse AM equals a lambda, which implies 1 by 1 blocks of Ji, the one we defined in the last lecture. In the general case, some eigenvectors are missing. Some eigenvectors are missing, and a diagonal form is impossible. And a diagonal form is impossible. So, for example, we will be using this matrix to find. We'll use this J to, for an example, and find the eigenvectors associated with A. So if J is of this form, 8 1 0 8 0 1 0 0 0. So if J is of this form, this implies J1 is a 2 by 2 block. Lambda 1 equals lambda 2 equals 8. J2 is, so again, a 2 by 2 block. Lambda 3 equals lambda 4 equals 0. And J3 is a 1 by 1 block. Lambda 5 equals 0. So this implies, because this is one Jordan block associated with this one, so it implies one independent or one eigenvector. One is always independent, one eigenvector. This implies one eigenvector, and this implies one eigenvector. This will have eigenvector x1. This eigenvector will be x3 because x1, then x3, and then finally x5. Okay, so there are 3 Jordan blocks, so imply 3 independent eigenvectors. 3 independent eigenvectors, which are x1, x3, and x5. So if A had, so this is A similar to J, so A is similar to J. So if A had 5 eigenvectors, then obviously we'll have a diagonal. If A had 5 eigenvectors, A had 5 eigenvectors, then all blocks would be one by one, and J would be equal to a diagonal. So since A is equal to M inverse, J is equal to M inverse AM. This implies MJ equals AM. So I multiply M over here, I multiply M over here, so I get MJ equals AM, or A times x1, x2, x3, x4, x5 equals M times J. This is M. Okay, so maybe I write J again. Let me write J again. So this is 8, 1, 0, 8, 0, 1, 0, 0, and 0. So I'm going to work with this one. So now, if you look at the first column is going to be A times x1. So what I can do is, I can write A here, 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 and I get rid of this A. So this implies the first column here equals M times this M is actually, this is not M now. This M is x1, x2, x5. So this first column here is going to be this one and this one, right? So AX1 equals 8 times x1, and AX2, the second column, is going to be this second column times this matrix, which will be x1 times 8x2. So 8x2 plus x1. Because this is x1y, because of this one, we are taking the previous column, and this is the previous column. So 8 corresponds to this one, and this one's and sum of all these. Similarly, this is 1, 2, 3. So AX3 equals 0x3, because there is 0 here. AX4, so AX4 would be this one because of x3 and this because of x4. So this will be 0x4 plus x3, and finally AX5 would be 0x5. So there are 3 genuine eigenvectors. 3 genuine eigenvectors in columns 1, 3. So 1, 3, and 5. 1, 3, and 5, and 2 generalized eigenvectors in columns 2 and 4 that are generated from column 1 and column 3 respectively. Okay. So x2 or x2 belongs to a string of vectors, headed by x1. x4 belongs to a string of vectors headed by x3. So it's this one x3 and this one x2. So this vector eigenvalue equation is a little modified, and now we have the present ax lambda x4 plus the previous one. Why the previous one? Because of this one, this one we have the previous eigenvector too. Okay, so so this implies the search for Jordan form, of A becomes a search for these strings of vectors, each one headed by an eigenvector, So for every I, either AXI equals lambda I xi, or AXI equals lambda I xi plus x of I minus 1. There is no lambda here, this is only 1. The coefficient here is 1 in the Jordan block, that's why this is I minus 1. And xi belongs to columns of m, where each string produces a single Jordan block, Okay, so now actually there is a lot of notation that may confuse you, but once we do the example, probably everything would be clear. Just remember this thing. So either this is equal to this when for the eigenvector case, and for the generalized eigenvector case, this is true. So if we have a Jordan block which is lambda 1, lambda 1, lambda, so this will be just ax1 equals lambda x1. This would be ax2 equals lambda x2 plus x1. So this will give you actually ax1 equals lambda into x1. This thing is going to give you ax2 equals lambda into x2 plus x1. And this one is going to give you ax3 equals lambda into x3 plus x2. Because of this one, you have to add the previous vector. Okay, so just keep this in mind. Either you have the eigenvalue equation, or for the generalized case, you have to add the previous one. So let me give you a computation algorithm, and then we're going to do an example, and hopefully we're going to do 2 examples, and hopefully things will be clearer after the 2 examples. So how do we compute? So computation of Jordan form. So let V V vector, let V be a generalized eigenvector, be a generalized eigenvector of grade K. Grade K simply means there are K there of grade K. Grade simply means K eigen K vectors exist or can generate K vectors. Can generate K vectors of grade K of matrix A of matrix. So let B be a generalized eigenvector of grade K of matrix A associated with lambda. And just keep in this mind that this block is always has the same eigen. So it's the repeated eigenvalue that is a problem. That's why we have a Jordan block. For distinct eigenvalues, this is not a problem. Associated with lambda. So let V be a generalized eigenvector of grade K of matrix A associated with lambda. Then this implies, and this is all only possible. So let V be a generalized eigenvector of K associated with lambda if and only if A minus lambda I raised to the power K into V equals 0. So this means V belongs to the null space of A minus lambda I K. This belongs to the null space of K. This, by the way, is called NK. So let's define this as NK is equal to 0 and A minus lambda I K minus 1 into V is not equal to 0. This simply implies V does not belong to the null space of K minus 1. Okay, so V belongs to the null space of A minus lambda I K, but V does not belong to the null space of K. So this is null space of A minus lambda I K minus 1. Okay, and then let's define Vk as V. Okay, then Vk minus 1 is simply A minus lambda I times V, which is actually A minus lambda I times Vk. Okay. Vk minus 2 is A minus lambda I square into V, which is equal to, this is equal to simply A minus lambda I into Vk minus 1. Because if I, instead of Vk minus 1, I put this one value, because Vk minus 1 is equal to this one, I will go back to this equation where Vk is equal to V. So continue on. So the final one is Vk is A minus lambda I into K minus 1 into V equals A minus lambda I into V2. So each one is equal to the previous one. If you see this one, this is equal to the previous. So Vk minus 2 is equal to, so this simply implies Vk minus 1 equals A lambda A Vk minus lambda Vk. So if lambda Vk comes on this side, we have the same equation. A Vk is equal to lambda Vk plus the previous eigenvalue, plus the previous vector. So this is why we have set it up, like we have defined it like this. And if you see, this one is simply Vi, which is by definition A minus lambda I into K minus I into V. So if this is I, this is K minus I, this is I, this is K minus I, same here. So this 2 is actually K minus 2. So K minus 2 is 2, because this is I, this is I, so this is, so this implies this one. Okay, so set of vectors. So let's define, so just say this is a fancy way of saying the same thing that we said. The Axi is equal to lambda I xi plus x minus 1. So this is exactly the same thing. So a vk is equal to lambda vk plus vk minus 1. So the set of vectors v1 to vk is called a chain of generalized eigenvectors. It's called a chain of generalized eigenvectors, generalized eigenvectors of length k, So another definition, Ni denotes, which I've already said above, denotes null space of a minus lambda I raised to the power I, and contains all x such that a minus lambda I raised to the power I into x equals 0. So this definition of x belongs to the null space of A. Also x belongs to the null space of a minus lambda I, and this implies null space of a minus lambda I raised to the power I is a subset of null space of a minus lambda I raised to the power I plus 1. Okay, and if I look at this equation, and I combine this equation with this one, what do I have? So a minus lambda I kv is equal to 0. So a minus lambda I k into v equals 0, and vi is, by definition, is a minus lambda I into k minus I into v, right? A minus lambda I into k minus I into v. Maybe I get rid of this underline from here. Okay, a minus lambda I k minus I v. So I can write this one equal to, if this is equal to a minus lambda I into k minus, or maybe a minus lambda I into a minus lambda I into k minus I into v equals 0. Okay, but what is this thing? This by definition is a minus lambda I k minus I into v. So this by definition is vi. So this implies a minus lambda I into vi equals 0. So this is how we are going to find vi. We are going to keep on finding the null space of a minus lambda I raised to the power I, and then eventually somewhere we'll stop, and I'll tell you where to stop. Also from here, what do we have? Also a minus lambda I into k minus 1 into v. So v does not belong to the null space of a minus lambda I k minus 1. This is not equal to 0. This implies, so this I can write as a minus lambda I into I minus 1 into I minus 1 into a minus lambda I into k minus I into v not equal to 0. And what is this thing? A minus lambda I ki minus vi. So this means, so this by definition again is vi. So this implies a minus lambda I raised to power I minus 1 into vi is not equal to 0. So vi belongs to the null space of Ni, but Vi does not belong to the null space of I minus 1. Okay, good. So now what do we do? So assume assume A has lambda with multiplicity m. So these mean there are lambda 1, lambda 2. So this implies lambda 1, lambda 2 equals lambda m equals some lambda. Okay. So you have m eigenvalues of the same lambda. So what we do is we compute. So this is the algorithm. So we compute rank of A minus lambda I for I equals 0, 1. This continues until rank of A minus lambda I equals n minus m. Why? Because this implies the nulls the nullity or the dimension of null space of A minus lambda I equals the number of columns minus the rank, which is equal to n minus m, which is equal to m. This is, by the way, called the nullity. So this is nullity. So nullity is the dimension of the null space. So that when the dimension of the null space is m, you stop. Why? Because this implies m independent eigenvectors exist. M independent eigenvectors exist. And where, or also, this also implies from here, this also implies the null space of 0 is subset of null space of 1 is a subset, so on and so forth. And this one, that's it. And the nullity is. So you keep on computing the rank of A minus lambda I for I is equal to 0, 1, up to such that the rank of A minus lambda I is n minus m. When the rank is n minus m, you stop. Why? Because then the dimension of the null space is simply m, which simply means you have the m required eigenvectors for each of the eigenvalue over here, or enough exists so that you can find the chain of eigenvectors. Okay, so if the nullity, so Vk is the dimension of null space of A minus lambda I k. So Vk is the dimension of the null space of A minus lambda I k. So if then this is m, this implies rank of A minus lambda I k is n minus n. Okay, so we need to compute. So compute this difference, the dimension. So this is the dimension of the null space of k. This is the dimension of the null space of k minus 1. So this is corresponds to null space of A minus lambda I k, and this corresponds to null space of A minus lambda I k minus 1. So you see how many vectors are there. So this difference is the number of vectors, number of eigenvectors in n k. So A minus lambda I k. So this number is k. If this number is greater than 1, this implies other eigenvectors other eigenvectors that generate their own other eigenvectors exist that generate their own strings their their own strings that generate their own strings. Okay, so what we want to do is we want to take this one, right, and uh, we say a minus lambda I. This is again the reiteration of the fact that of this algorithm, reiteration of this algorithm again. So a minus lambda I k and a minus lambda I k times some u or v, whatever you want to call, is 0. This implies where uk or vk, maybe we want to do the same thing, maybe we just say vk, maybe we just say v, where v equals vk equals v. Okay, and then we say vk minus 1 equals, and what is vk minus 1? vk minus 1 is equal to a minus lambda I vk, and so on and so forth until v1 is equal to a minus lambda I k minus 1 v. So a minus lambda I, and vk minus 1 is equal to a minus lambda I into vk goes on until v1 equals a minus lambda I into k minus 1 into vk. vk or v, it's one and the same thing. So this implies a minus lambda I into v1. So a minus lambda, if I multiply a minus lambda here, I multiply a lambda here. So this is simply equal to a minus lambda I k into vk, or just v. V or vk is one and the same thing. V, because vk is equal to v, is equal to 0, or this implies, from this equation, this implies a v1 equals lambda times v1. Okay, and if I do a minus lambda I v2, this would be equal to a minus lambda I into k minus 1 into a minus lambda I into k minus 1 so k minus 1 into v, which is equal to what? So what is a minus lambda I into k minus 1 into v or vk? It's the same thing here. So vk is same as v. This is v1, this is v1. So this implies from here, if I compare these two, this implies a v2 equals lambda v2 plus v1, and so on and so forth, right? And finally, so this goes on until a minus lambda I vk, equals a minus lambda I which is a minus lambda I v, which is simply equal to vk minus 1. So this is over here, a minus lambda I vk, which is equal to a minus lambda I vk minus 1. So this implies a vk equals lambda vk plus vk minus 1. So in all cases, either we have the eigenvalue equation or we have the eigenvalue equation plus the previous one. So this is the previous vector because of ones above the main diagonal. Previous vector because of ones above lambda, right? And this is again the previous one because of the ones above the main diagonal. So So this implies my matrix, my matrix, my matrix Q, or maybe M, I think I should call M. M should be of this form. This should be of U1 or V1, I'm sorry. This should be of V1, V2, and so on up to Vk. And then I have another string, maybe W1, and goes on and so on and so forth, right? So first string, second string, and maybe I say so on and so on. So this is what we want to get. And to show how do we do that, let's do an example. So we're going to do two examples, and we're going to do these steps in all the examples so that it's clear to you how to compute the joint form. So A is equal to, let's say A is equal to this 1, 2, 3, 4, 5. 8, 1, 2, 3, 4, 5. Then I have string of zeros, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. And then I have 8, 8, 0, 0, 0, 0. And then I have 8, 8, 0, 0. I have 4 zeros. I'm sorry, I don't have this one. 8. So I have, this is the eigenvalue, this is the eigenvalue, this is an upper triangular matrix, eigenvalue, eigenvalue, eigenvalue. So this implies lambda 1 equals lambda 2 equals 8, lambda 3 equals lambda 4 equals lambda 5 equals 0. So this is a 5 by 5 matrix. And I can see the rank. So there are two zero rows. So two rows of zeros. So 2 rows of zeros. So this implies the rank of A equals 3, right? It's 1, 2, 3. Rank of A equals 3. So this implies, and since if I do A minus 0i, and since A minus 0i, or no, so this implies rank is equal to 3. This implies the nullity, which is the dimension of the null space. So nullity, which is the dimension of null space of A, equals n minus the rank, which is equal to 5 minus 3 equals 2. Right? So there are two eigenvectors, but since also we can also note here also A minus 0i equals A, this implies for lambda 3, lambda 4, lambda 5 equals to 0, there exist only these two independent eigenvectors. So we have to find one more, right? Okay, good. So let's start with this one. So if lambda 1 equals 8, this implies A minus 8i equals, so I subtract 8 from the diagonal, 0, 0, 0, 0, 0, 0 minus 8, 0, 0, 0, 0, 0, minus 8, 0, 0, 8, 8, 0, minus 8, 0, 8, 8, 0, 0, 0. Okay. If I do, so let me find the rank of this one. So I do minus row 1 plus row 2. If I do minus row 1 plus row 2, I can get rid of these two. And then if I do, so let me do this. So this will be 0, 0, 0, 8, 8, 0, minus 8, 0, 0, 0. And then I do 1, 2, 3, 4. And if I add row 4 and row 1, if I add row 4 and row 1, what do I get? And if I add row 4 and row 1, 1, 2, 3, 4, row 4 and row 1, so I'll get an 8 over here. Is that right? Oh, let me do that. So, and if I add, okay, let me do it first. So 0, 0, minus 8, 0, 0. So it's only this operation. 0, 0, 0, minus 8, 0, 0, 0, 0, 0, 0. Now I want to get rid of this 8, so I do row 4 plus row 1. If I do row 4 plus row 1, this minus 8 goes there. This is 0. So now I think I have pivots. So I have this pivot 1, I have this pivot 2, I have this pivot 3, I have this pivot 4. So this means implies the rank of A minus 8i, A minus 8i is 4. This implies the nullity, I'm not going to write again the dimension of the null space. So the nullity is 5 minus 4, which is equal to 1. So we only have one eigenvector. So I have to, and what is that eigenvector? So 5 minus 4 is equal to 1. This implies the eigenvector is, so the free variable is the first one, all other are pivot variables. This implies this eigenvector is 1, 1, 2, 3, 4. Okay. So this is the eigenvector in null space of A minus 8i. Okay. Since this is only one, I have to do A minus 8i square so that I can get more eigenvectors. So let's do A minus 8i square. And A minus 8i square is, I simply take this matrix, not this one, I take this one and multiply it. So 0, 0, 0, 8, 8, 0, minus 8, 0, 8, 8, 0, 0, minus 8, 0, 0, 0, 0, 0, 0, minus 8, 0, 0, 0, 0, 0, 0. Multiply by the same matrix. So 1, 2, 3, 8, 8. 0, minus 8, 0, 8, 8. This is a straightforward procedure, but it's just time consuming. So you just have to be patient and pray that you don't mess up with the calculations. 0, 0, minus 8, 0, 0, 0, 0, 0, 0. So if I multiply these two, what do I get? Again, still a 5 by 5 matrix. So this means I'm multiplying the fourth and the fifth row by 8, and then adding. So fourth and fifth row, first are 3 zeros. No problem here. This is minus 64, and this is still 0. Okay, good. Or maybe I do the easiest ones first. So third one means I just multiply the third row by minus 8. So third row by minus 8 means this will become 64. So 0, 0, 64, 0, 0. This means the fourth row is being multiplied by 8. So I have 0, 0, 0, 64, 0. Good. And this means there is no contribution. 0, 0, 0, 0, 0. Okay. Good. So what about the second? So now the second row is multiplied by minus 8. The fourth and the fifth are multiplied by 8, and they are all added together. So second row, and maybe this is an easier way to do it. So second row, no change here, 0. This is minus 8 is 64, nothing here. So 64, nothing here, 0. This is minus 64. This is minus 64. This is minus 128. And the last one is minus 64, and that's it, minus 64. Okay, good. And if I do the reduced row echelon form just to see what is the rank here and what are the eigenvectors, so let's see. What do? I do 2 times row 4 plus row 2. 2 times row 4 plus row 2. If I do that, so 2 times row 4, and I also do row 4 plus row 1. Row 4 plus row 1. If I do row 4 plus row 1, this will go to 0. So 1, 2, 3, 4, 5 zeros here. Good. Last row is same, nothing changes here. Third and fourth is same, 0, 0, 64, 0, 0, 0, 0, 0, 64, 0. So when I do 2 times row 4, so 0 and 64 don't change. So this one goes away, 64, 128 minus 128, 0, and this is minus 64 as is. I can divide everything by 64 and I can get 1. And then I do row 2 by 64. I do row 3 divided by 64. I do row 4 divided by 64. If I do that, this will become 1. This will become 1. This will become 1. And this will become minus 1. Okay, good. I have one pivot here. I have one pivot here, two. I have two pivot here. I have a row of zeros, So the rank of a minus 8i squared is 2, This implies the nullity of this one is 5 minus 2. Sorry, 1, 2, 3. This is 3. I'm sorry. This is 3. So nullity here is 5 minus 3, which is equal to 2, and this implies there are 2 independent eigenvectors. Very good. And now we can stop. Why? Because lambda is equal to 8 is repeated twice. So lambda is equal to 8 is repeated twice. So all we needed was 2 eigenvectors. So good. Now so let me see what are the eigenvectors. So what are the 2 eigenvectors? So the 2 eigenvectors are 2 eigenvectors in null space of a minus 8i squared, right? And they should not be in the null space of a minus 8i. Are, and what are those? We pick this column or we just write it. So forget about it. So let's write it. So where are the free variables? So the free variable is first one, 1 and 0, and the free variable is the last one, 0 and 1. Okay, and in between, so second one, this one is the last one. So this is plus 1, minus 1 goes here, becomes negative 1, and everything else is 0. 3, 4, 3, 4. So these are the 2 vectors, but we are going to pick the one. So pick one, pick the vector that is not in null space of a minus 8i, and that vector is, so if we look at this vector, so this is the vector, so this vector is exactly the same as this vector, so we are not going to pick this one, we are going to pick this one, right? So we say, so this implies from our notation, we say v2, because it's a string of 2, equals 1, equals 0, 1, 0, 0, 1. So v2 is equal to this one. Pick the vector that is not in this one, and which means this one. If this is true, then we know a minus 8i into v2 into v a minus 8i into v2 should be equal to v1. Why? Because a v2 equals 8v2 8v2 plus v1, right? So a minus 8, so v2 is this one, the one from the eigenvector corresponding to the null space of a minus 8i square. So that's why, because of this 2, we call this 2. And then we say v1 is this one. So what is v1 then? So this implies v1 is, and what is a minus 8i? So let me get a minus 8i. So this is a minus 8i. So maybe I just copy this one. Let me see. How do I copy this one? I copy this one like this, and then I say, I think I also have to say copy. Yeah. So I copy. I think this is the copy one, and then I say, I maybe say paste. Paste. Good. Okay. So this is a minus 8i, into v2. Sorry. Into v2. I think this one. Into v2, which is 0 1 0 0 1 0 1 0 0 1. And if I do that, this is simply equal to, I am picking the second column and I'm picking the last column. If I do that, this becomes 0 and 8 is 8, minus 8, 8 is 0, 0, 0 is 0, 0, 0 is 0, 0, 0 is 0. So this is v1. This is v1. So we have v1, we have v2 corresponding to eigenvalues of 8. Good. Okay. Now we need to find the eigenvectors for corresponding to 0. So for lambda is equal to 0, if you recall, for lambda is equal to 0, we had two independent eigenvectors. And what were these two independent eigenvectors? These two independent eigenvectors were, if you go back here, so what were these two independent vectors? So these were picking the second column and picking the third column. So these are the two independent eigenvectors. So if I do that, so this will be, so these two independent vectors, we have two independent eigenvectors. These were picking the second column and picking the third column, right? Because if I pick the second column and the third column, if I multiply a times this one, it will be 0. If I multiply a times this one, this will be 0. So these are two eigenvectors. And these two eigenvectors, we have two eigenvectors in null space of a minus 0i. This is in the null space of a minus 0i. So let's calculate. And what was the rank here? The rank here was, so if the null space is, dimension is, so dimension of null space of a minus 0i was 2. This means rank of a minus 0i was 3. Okay. Okay. So let's do a minus 0i square. So a minus 0i square is simply a square. This is simply a square. So let me do a square. So a square is 8, 0, 0, 8, 8, 0, 0, 0, 8, 8, 0, 0, 0, and I have 0, 0, 1, 2, 3, 1, 2, 3, 4, 5, 8. And if I multiply these two together, so this is 8, 0, 0, 8, 8, 0, 0, 0, 8, 8, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 8. And what is this equal to? This is equal to, again, I am looking at the first row and the last two rows. So the first row and the last two rows, all are multiplied by 8. So 64 here, no contribution here, no contribution here, 64 here, and this is 64 and 64, 128 here. Okay, and this one contribution is in the last two rows. So last two rows except the last one, everything is 0. So 0, 0, 0, 0, 64. And this one, no contribution, no contribution. So 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. And this one, last row, this is 64. So I can get rid of this 64 and I can get rid of this 128. So I do row echelon form. I say minus row 1. Sorry. I say minus row 5 plus row 2, and I do minus 2 times row 5 plus row 1. So this will become then 64, 0, 0. This will be still 64. This will be minus 128 plus 128, 0. This will be 0, 0, 0, 0, 0. Why? Because minus 64 plus 64, everything else is 0 here, 0 here, and then 0, 0, 0, 0, 64. What I can do is, let me draw a larger square bracket. Okay. Then I say do R1 divided by 64 and do R5 divided by 64. If I do that, this is 1, this is 1, okay, and this is 1. So 1, this is a pivot, this is 1, this is a pivot. So now the rank is 2 and nullity is 5 minus 2, which is 3. So we have 3 independent eigenvectors. Excellent. So implies 3 independent eigenvectors. If we have now 3 independent eigenvectors, and what are these 3 independent eigenvectors? These are 1, 2, 3. So where are the free variables? The free variables are second, third, fourth. So second, third, fourth are free variables. Second, third, fourth. These are the free variables. And then I have this one, 1, 2, 3, 4. Second, third, fourth. So this is minus 1. This is 0. This is 0. So this one goes here, becomes negative minus 1. This is all row reduced echelon form, 0, 0, 0. Right? So I have this one, and this one. Now, these two, when we are picking the second column and third column, they are already here. They're already here. So we can't pick these two already in null space of A minus 0i. So can't pick these two. So this is the one. So since this is a string of 3, so I say, so V2, maybe I say now U2. So U2 equals minus 1, 0, 0, 1, 0, and this is in null space of A squared. And this is not in the null space of A. Okay, if this is in the null space of A square, so again we do the same thing. U1 equals A minus lambda I into A minus lambda I into U2, right? So because this will give me A U2 equals lambda U2 plus U1, and so what is U1? So this implies U1 is simply A minus actually lambda I or 0i. Maybe I say this is 0i. So U1 is simply A U2. And what is A U2? So I am picking the 1, 2, 3, 4. I'm picking the fourth column and subtracting the first column from there. So picking the, where is A? So this A. So picking the fourth column and subtracting this one there. So 8 minus 8 is 0. And so we have 0, 8, 0, 0, 0. So we have 0, 8, 0, 0, 0. But this vector is the same as this vector. It's only the same. This is the same vector. So this is the same vector. So this implies the third vector. So this is the third eigenvector corresponding to lambda equals 0, and this is simply 0, 0, 1, 0, 0. Okay, this one. So now I have m. So now I have m. So this implies my m is v1, v2, then I have u1, and I have u2, and then I have w. Why have I've selected like this? Because this will give me a Jordan block of 2 by 2. This will give me a Jordan block of 2 by 2. This corresponds to lambda 3 equals lambda 4 equals 0. This corresponds to lambda 1, lambda 2 equals 8, because this is the J I was given. And this is the Jordan block, which is 1 by 1, and this corresponds to lambda 3 equal to 0. So if I do that, so let me check, do I get the same thing or not? So my m is, so this implies my m is, so v1, v2, v1, v2. Where is v1? So my v1 is 8, 0, 0, 0, and this is 0, 1, 0, 0, 1. So 8, 0, 0, 0, 0, 0, 1, 0, 0, 1. And then I have u1. u1 is 0, 8, 0, 0, 0, 0, 8, 0, 0, 0. u2 is minus 1, 0, 0, 1, 0, minus 1, 0, 0, 1, 0, and finally this w is 0, 0, 1, 0, 0. 0, 0, 1, 0, 0. Obviously, I am not going to find the inverse of this thing, but since m inverse is equal, sorry, m inverse am equals j, so what I'm going to do is I'm going to multiply m here, I'm going to multiply m here, and I'm going to show am equals mj. So I would suggest that at home you show that am, which is 8, a is 8, 0, 0, 0, 0. Then I have 0, 0, 8, 8, and I have 0, 0, 8, 8, and then I have string of zeros, and I have another string of zeros except the last one. A times this m, which is 8, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 8, 0, 0, 0, minus 1, 0, 0, 1, 0, 0, 0, 1, 0, 0. You show that this am is what? And show that this is equal to m times j, where m is this matrix 8, 0, 0, 0, 0. So I'm not going to do that for you, you're going to do it yourself. 0, 8, because it's simply matrix multiplication and I don't want to do it. Minus 1, 0, 0, 1, 0, 0, 0, 1, 0, 0, and multiply by j. J is like this: 8, 0, sorry, 8, 1, 8, 1, 8, and then I have 0, 1, 0, and then I have 0. Okay, so if you multiply this out, you are going to say, so maybe this is some x, this is some y, and you're going to see that these two are equal, same. So this m will give us this Jordan form. So one Jordan block of 2 by 2, one Jordan block of 2 by 2, and one Jordan block of 1 by 1. So let me do another example before we finish this chapter, and that example is A equals, it's a smaller matrix now, 0, 1, 2, 0, 0, 1, 0, 0, 0. So what are the eigenvalues? 1, 2, 3. So lambda 1 equals lambda 2 equals lambda 3 equals 0. So there are 3 eigenvalues, and the rank here is 1, 2. So rank of A is 2, which means the nullity is or nullity of A A1 A actually. Nullity of 1 is simply 3 minus 2, which is 1. So it implies 1 eigenvector. And what is that eigenvector? This eigenvector is, you simply select this one because this is the free variable. So 1, 0, 0. Okay. So let's do a minus 0 I square, which is simply a square. A square is 0, 1, 2, 0, 0, 1, 0, 0, 0 multiplied by 0, 1, 2, 0, 0, 1, 0, 0, 0. When I multiply these together, what do I get? I'm changing adding the second row twice the third row. So second row 0, 0, no change. This is 1, 1 here. Then I'm picking the third row. The third row is all zeros. And then I'm picking again the third row, no contribution, so this is 0. So here the rank is 1. Rank is 1, and the dimensionality of the null space is 3 minus 1, which is 2, and we have 2 eigenvectors. And what are those 2 eigenvectors? So 2 independent eigenvectors, and those 2 independent eigenvectors are, if I pick this one and this one, the free variables are in the first and the second one. So first and second, 1, 0, 0, and then I have 0 and 0. Okay, so these are the 2 eigenvectors. This is already in here. So again, I need 3 eigenvectors. So let's do a minus 0 I cube, which is a cube, which is equal to a square, which is 0, 0, 1, 0, 0, 0, 0, 0, 0. Doesn't make a difference whether you do a square, a or a times a square. This is 0, 1, 2. This is much easier. So 0, 0, 1, 0, 0, 0. And this is a matrix of zeros. Why? Because I'm putting the third row, which is zeros, and there is no contribution. So rank here is 0. This implies the nullity is 3 minus 0, which is equal to 3. So this implies 3 independent eigenvectors. And what are those? Those are 1, 0, 0. You pick the first column, or you pick the second column, or you pick the third column, right? So 0, 0, 1. Now these two are in here. So this is the one that I'm going to pick. So I'm going to say W3 equals, so this W3 is not in null space of a square. So this implies W3 is simply 0, 0, 1. And I'm going to use W3 to generate W2 and W1. So what is W2? So W2 is simply A minus lambda I into W3. Why is this? Because this implies A times W3 is equal to lambda times W3 plus W2. And this implies, what is W2? W2 is simply A is 0, 1, 2, 0, 1, 2, 0, 0, 1, 0, 0, 0 times W3, which is 0, 0, 1. So I'm picking the third column. This is equal to 2, 1, 0. Okay, so this W2. And what is W1? And W1 is simply A minus lambda I into W2, because A times W2 is equal to lambda times W2 plus W1. And this one is equal to, again, 0, 1, 2, 0, 0, 1, 0, 0, 0 multiplied by my W2, which is 2, 1, 0, and this is equal to, so twice the first column, no contribution, and once the second column. So this one is this one is, and there is no contribution of the third one. So this is 1 and this is 0, this is 0. Okay, so my m is, so this implies m is w1, w2, w1, w2, and w3, which is equal to 1, 0, 0, 2, 1, 0, and the third one was 0, 0, 1. 0, 0, 1. Again show AM. What is AM? AM is 0, 1, 2, 0, 0, 1, 0, 0, 0 times M, which is 1, 2, 0, 0, 1, 0. This I can do for you because this is much simpler, is equal to M times J. Now J is what? J has only one independent eigenvector. So this is only a block of this is only a block of 1, 0, 0, 0, 1. There is only one eigenvector. So there's only one eigenvector. So this is one Jordan block. So one Jordan block. One Jordan block, because there was only one eigenvector in the beginning, right? So what is M? M is 1, 2, 0, 0, 1, 0, 0, 0, 1. So if I multiply these out, I will get, so again, contribution of first, second row and third. So 1 here, so 0 here, 1 here, 2 here. Pick the third row, and then there is no contribution. And what is this one? So first row and then twice second row. So 0 here, first row, twice row, pick the second row, and pick the last row. And if you see, both of them are same. So this Jordan block is all right. So this is all right. Okay. So where is the application? So the application is to the differential equation or the difference equation, which we have already seen. So application is du over dt equals au for u is equal to mv. This becomes m times dv over dt, which is equal to a times m times v, which is, or dv over dt is equal to m inverse am times v, and this is, by the way, the Jordan form. Okay, so this is equal to jv. Similarly, we can show it for the difference equation, and we have completely off. So we have this implies we have coupled uh, off diagonal ones within each, or maybe we just stop here. So this is because of ones on main diagonal, because of ones above main diagonal. We have all of ones above main diagonal, because once we have above main diagonal, we have coupled differential equation. We have coupled differential equations. Okay, so this is all we want to do from chapter 5. Please review this Jordan form carefully, because if the matrix does not have a full set of eigenvectors, the only way we can diagonalize it is by the Jordan form. And this is a step-by-step procedure. All you need to do is find the rank of a minus lambda I raised to power I, and compute it until the null space has enough eigenvectors, and then you can compute. And the only thing that you need to check is the eigenvectors in the null space of A minus lambda I raised to the power I should not be in the null space of A minus lambda I raised to the power I minus 1 in the subsequent null space. So once you do that, the process is straightforward. And if you have any questions, we can discuss on Mondays or Wednesdays, or you can also email me. So there is only one chapter left, and that chapter is on singular value decomposition. What happens if the matrix is not square and rectangular? So that's the general problem, which is the general problem, or we can say this is a superset of the eigenvalue problem, which is only for square matrices. What happens if you have a rectangular matrix, and over there we have singular value decomposition, and we probably have couple of lectures, probably 2 lectures on singular value decomposition, and then we'll finish off this course. Okay. Thank you.